Okay, so welcome back. So today we've got three goals in mind. So we're going to probably wrap up some ideas that relate to the atom today. Specifically, we're going to look at special kinds of atoms, fancy word called radioisotopes. Uh, you'll take a look at the definition of that along with half-life in this lesson. We'll identify three ways that what we call radioisotopes are actually used in the world, so you can see that there's some usefulness to them. And then some basic calculations that relate to the decay of radioisotopes. Decay meaning the nucleus turns into new atoms. You recently did some lesson work that shows two kinds of decay, one called alpha decay, one called beta decay, where the nucleus of an atom, we were calling it the parent, turns into smaller fragments. And those smaller fragments add up to the initial nucleus of the atom that we called the parent. So let's move forward. So what I'd like us to take a quick look at is some key terminology. So before we get started with the lesson, let's get rid of my face here. Here we go. And key terms, well, one of the things we're going to take a look at today is a word we haven't used. It's called a radioisotope. It generally means an atom that naturally undergoes decay. So the nucleus is unstable and it will naturally break apart or fragment to turn into something more stable. Usually releases radioactive material or radioactive particles or radioactive energy. So it releases what we know as ionizing radiation, alpha, beta, or gamma radiation. A review of a key point, what's the cause of radioactive decay? Well, radioisotopes, they break down because their nucleus is unstable. And that relates to the proton to neutron ratio, which we've covered in previous lessons. And something that we didn't speak about is the process, what causes it. In many cases, it is natural. But what scientists have learned to do is they have learned to artificially cause this to happen. And that allowed us to use it in more practical ways to make an atom's nucleus decay and then harness that energy sometimes for doing things. Okay, so that's sort of the key point about what the cause is of nuclear decay. It goes back to that unstable nucleus, the ratio of the proton and neutron count. So what we say then about the nucleus, some atoms have a stable nucleus because the proton to neutron ratio favors stability. Some atoms have an unstable nucleus, and those ones that would naturally decay, we call them radioisotopes. When they decay, they'd release what we call ionizing radiation. I believe what they're showing us here is a beta particle being released. And something we really didn't talk about is the enormous amounts of heat energy that are released as radioisotopes decay. Moving forward, there are some practical uses for atoms that naturally decay or artificially decay. One of them would be radiation therapy, where we direct a beam of radiation directly at cancerous cells to destroy those cancerous cells. What scientists have figured out is how to make that beam very accurate, because not only would it kill cancerous cells when it comes in contact with cells, it would also kill the normal cells. And radiation therapy over the years has become much more accurate. So now they're saying they can do radiation therapy with pinpoint accuracy. They can get it at the cells that need it and salvage most of the cells that don't need it. It's also used in medical diagnoses. There's an isotope called sodium-24. You would ingest it, or it would be injected probably into your bloodstream. And that would allow them to do what we call radiographic imaging. They would, by using special sensing equipment, they could determine where blockage might be or abnormalities in the circulatory system. So radioactive materials are sometimes intentionally placed in the body for medical diagnosis. There are lots of different radioisotopes used in lots of different forms of medical diagnosis. This is just an example. Here's an interesting one, food irradiation. Intentionally exposing food to radioactive material to kill bacteria, viruses, germs. So it's a way to sterilize prepackaged food. Oddly enough, some prepackaged food is sterilized this way. That way it makes it, in terms of bacteria, um, sort of bacteria free and much safer to eat as a result. The dating of artifacts, we can determine how old an artifact was as long as it contains formerly living material on it. Usually we call those fossils. So there's a test called carbon-14 dating. We won't get into the details of it, but it uses carbon-14, a radioisotope. Here's an interesting use for thickness gauge, where they'd actually divert a beam of radioactive particles at a continuously rolled product. Sometimes when paper is manufactured, it's manufactured in a continuous roll form. And as it rolls through the line, right, that what they'll see is they'll roll it back up on the end of the line. So at one end of the line, they're spreading this long sheet of paper out. On the other end, they start rolling it back up. Well, with a radioactive sensor on one end and a radioactive source on the other end, they can determine by how much radioactive material has made its way through, how thick the material is, and make adjustments while they're manufacturing. So that's an interesting use for radioisotopes. Now we'll get to the skill part of today's lesson, learning how to. So before we can do that, we got to just cover a few basic facts. Here's a chart that shows what we would call half-life. And half-life is a time, what we would describe it as the time needed for 50% of the particles, sometimes we call that the mass, of any radioisotope to decay. You can see the times vary. For lithium-8, it's 0.8 seconds. For krypton-89, it's like 3 minutes. For sodium-24, 15 hours. Look at this for uranium, 700 million years. So that relates to how stable or unstable these nuclei are. The more unstable they are, the quicker they break down. The more stable they are, the generally, longer a half-life time might be. I'm generalizing here. So these times vary greatly, which is what I just said. Every radioisotope, which they're calling a radioactive nuclide here, which means nucleus. The nucleus is radioactive, so what does it do? Decays. So this is really just a table. We're not memorizing this. So it just gives us some ideas that the times vary greatly depending on what radioisotope we're talking about. Now we get to the skill part of today's lesson. So there's a context. We'll talk about the context in a moment. What we're going to do with the context is we're going to build a table. There are other ways to do this. I like this table format because it's very simple. It really involves just some basic math, and it's a nice, easy, organized framework for doing this. So what you'll want to do is construct a table. The table will have in it total time expired. That's how much time has passed. The number of half-lives expired. That's how many times the half-life has gone by in time. We'll explain that as we go through. The mass of radioactive material remaining, and the percentage of the radioactive material remaining. So to get started, what we do is we always start at time 0. So what I mean by that is the total time expired when we start, we will always put 0 in here. So I'm going to put a 0 in there. And we always start with the original mass. Well, we read for the words for a mass given. So it says here, a patient ingested, which means they ate or they drank it, 2 grams. There's your mass, 2 grams. So the mass remaining would be 2 grams at time 0. Before any of the material has decayed, all of it is left. So none of the half-lives have gone by in time 0. Half-lives have expired. The remaining mass is 2 at the beginning time of 0. So that means 100% of the material called sodium-24 is still radioactive. Well, look at, if we read further in the context, it says sodium-24 has a half-life of 15 hours. That means once 15 hours goes by, 50% of this mass, this 2 grams, is no longer radioactive. So what we'll do is we will add the half-life time. The half-life time is 15 hours to the total time expired. So we started at time 0, we're going to add 15. Now the total time expired is 15 hours. The number of half-lives expired at that point, at 15 hours, one half-life has passed. So once one half-life passes, what happens is half of the material that we began with remains radioactive. So we cut it in half. 2 gets cut in half. Now there is 1 gram of radioactive material remaining, which means it's no longer 100% radioactive. Half of the percentage is remaining. So half of 100, 50% of the material remains radioactive, or 1 gram of the original material, 50%. So we're just cutting these 2 columns in half. Okay, so what we're trying to do is we're trying to find out after 75 hours, how much would remain in the body? What would the mass be after 75 hours? Well, we've only reached 15 hours in time. So we might want to recognize that this time right here is actually a time in hours. That's useful for our recognition. So I'm going to put the little label hour right here. We might also want to recognize our mass is a gram amount. So I'm going to just put that little label so we're aware that's what we're looking for. Okay, now we go back and we add the half-life time to the total time. Remember, the half-life is 15. So now we add 15 to the 15 hours that have already expired. And that makes 30 now. That means 2 total half-lives have gone by, right? 2 times 15 makes the 30. What are we going to do to the mass remaining? Well, it's called half-life. That mass remaining gets cut in half. So now there's no longer 1 gram of radioactive material remaining. There's half of that, 0.5. What are we going to do to the percentage that was remaining? Well, half of that now remains. So we cut that in half. Again, mass remaining and percent remaining, we cut those in half. So we have not reached 75 hours, so we keep moving forward. We add the half-life time, 15 hours. That means 3 half-lives have expired. 3 times 15 made the 45. What are we going to do with 0.5? Well, it's called half-life. That mass gets cut in half. Now there's only 0.25 grams of radioactive. See, the radioactive material is decaying. There is very little left over at this point. What are we going to do with the 25% that was remaining? Cut it in half. Only 12.5% of the original material, the original 2 grams, remains. So we continue forward. What do we do to total time? Add 15, right? That's the half-life. 60 hours have passed. That means 4 half-lives in time have expired. We go back to the column over here where mass is, cut that in half, 0.125. We go over to the percentage remaining, cut that in half, 6.25. Notice we still have not reached 75 hours. Now we add 15 again to the total time. 75 hours have expired. That means 5 half-lives. 5 times 15 made the 75. I just want you to see where that came from. Cut 0.125 in half, you get 0.0625. Cut 6.25 in half, you get 3.125. So what have we just learned? We've learned that when 75 hours of time pass, the mass that's going to remain is right here. We just answered the question. What's going to remain is 0.0625 grams. If it asks what percentage remains, we would say 3.125% remains, but it asks for the mass that's remaining. So this is our answer. So after 75 hours of time, there's only 0.0625 grams of radioactive material remaining in this person. Remember, this was placed in this person's body. We don't want it to stay there very long. So right now, there's very little of the material left over. Okay, let's move on to another context. We're going to do the same thing. We set the table up in the same format. We'll clear the drawings here. New context, now it's krypton. Hey, look, krypton has a different half-life. Now it's only 3 minutes. Very quick half-life. The original mass that we're beginning with is 50 grams. They want to know after 3 minutes, they want to know after 3 minutes how much has decayed in percentage. So now we want to know the percentage of the radioisotope that would remain after 12 minutes. Well, let's see how we do that. Remember what we said, always start at time zero. Time zero, no time is expired. That means no half-lives have occurred yet. That means the mass remaining is the original mass, and that should be 50. Let's pause for a second and we'll make a correction here. Here we go. All right, so let's slow it down for just a second and emphasize some of the critical information. Identify the half-life, the time, 3 minutes. Identify the mass of original material you're starting with, 50, right? Identify how long it says we're worried about decay. Well, 12 total minutes. So again, we go back to always start at time zero. That means no half-lives have expired yet. So what we then do is we fill in the mass remaining. Since none of it had, no time has expired yet, all of it remains radioactive, 50 grams. 100% of it remains radioactive. So we fill in percent remaining. Okay, now to get started, what we do, we said we add our half-life, the time it takes to decay. So we add 3 because it's 3 minutes. Well, that means 1 half-life. 1 half-life is equivalent to 3 minutes. The mass remaining, remains, so it's called half-life. It gets cut in half. Now only 25 grams of it is remaining. Cut the percentage in half, 50% of it is remaining. Move forward. Look, it says after 12 minutes. We only reached 3 minutes of time, so we keep moving. Okay, so again, we add the half-life. So since we're adding 3, the half-life time is 3 minutes. 3 plus 3 becomes 6. That now means that 2 half-lives have expired. If you wanted to know where that 6 actually came from, there's another way to think about it. 2 half-lives, 2 times 3 makes 6 minutes. I like to add as you go down the columns. It's just easier to think about it when we first learn it this way, I think. So what'll happen to mass remaining? It's called half-life. It gets cut in half. Half of 25 is 12 and a half. What'll happen to percent remaining, right? It decays. Now only 25% of it gets cut in half. So we continue forward because we didn't reach 12 minutes yet. So we add the half-life time again, 9. After 9 minutes, that means 3 half-lives have expired. What mass would be remaining? Well, half of 12 and a half. That would be 6.25 grams. Half of 25%, 12.5%. Okay, so we've completed filling that in. We continue forward, right? Continuing forward, well, we got to reach 12 minutes, right? So in order to reach 12 minutes, right, time expired, we're going to have to add 3, right? 12, 4, right? That'll be 4 half-lives. 4 times 3 makes 12. Well, what would be half of 6.25? Well, that would be 3 goes into that, right? So half of 6.25, right? 3.125. 3.125. Let's make it look like a 5. Kind of hard to draw with this little goofy looking pen. And then half of 12.5%. 6.25% would be remaining. So what do they want to know? They want to know what percentage of it remains. So if I want to identify my answer now, my answer is 6.25%. So we've just figured out the percentage remaining using the same format as we did for the previous example. One more quick example. Clear the drawings, new context. Now it's uranium. Look for the key details, right? Key details. How much are you beginning with? Well, you're beginning with 30 grams. What's the half-life? Whoa, look at that, 700 million years. That's a long time. So how much is it going to decay till? Well, it's going to decay until there's 1.75 grams of it remaining. So look what they're asking us now. Now they're asking us how long. Now we're solving for a time. We can use the same table. We're going to solve for the time piece of the table now. Same table set up, right? Always start at time 0, right? At time 0, none of it has decayed. That means no half-lives have expired. That means 100% of it is still radioactive. So all of the uranium we started with, right, it's all radioactive. So what we need to do is we need to make it decay until we find out the information that we're interested in. Okay, another quick edit here. 30 grams is what we have to begin with, not 50. So 30 grams is the material we have to begin with. 100% of it is still radioactive at time 0. What are we going to do to get started? Add the half-life. 700. I'm going to use the number 700. We're just going to assume we know that means million when we're done. So number of half-lives at that time is 1, right? At 700 million years, that's 1 half-life. Half of 30 will be remaining, which is, voila, 15. Half of 100%, 50%. Continue moving forward. We want to find out until 1.75 grams of it remains. So we continue decaying, right? So our next decay would be at 1400, right? That'll be 2 half-lives. At 2 half-lives, 7.5 grams is remaining, half of 15. 25% of it is remaining. Okay, so now we're ready for our third half-life, right? We're going to add 700. Notice all we're doing, each time we move down a row, we add 700, 700, 1400, 2100. That means 3 half-lives have expired. Well, what'll happen to 7.5? It decays. 3.75 grams is remaining. So if 3.75 grams is remaining, 12.5% is what is left. Okay, let's keep our eye on the target here. What we're trying to find out is how long it would take until 1.875 grams of radioactive material remains. So we continue forward. We're going to add 700. That gives us 2,800 million years. That would be 4 half-lives. Half of 3.75. Ding, ding, ding. 1.875. That's the amount that we were looking for, right? And the percentage that would be remaining would be 6.25%. So if we go back to what the actual words were asking us about, it asked how long. So how long did it take for this decay to happen? Well, it's not actually 2,800, it's 2,800 million. So we want to identify our answer as 2800. And we want to make certain that we said it is million. So 2,800 million, that's a long time. One of the dangers with radioactive materials is some radioactive materials have very long half-lives, which means there's risk of exposure over time for a very extended period of time. So those are the goals for today's lesson. I hope you found it useful related to the specific goals. I'm going to ask you to maybe just do a couple of examples that relate to half-life style calculations. Use this model. If you've come up with another strategy that seems to work, look, I'm open-minded, but this strategy is a nice organized one, and I hope that you can find some success with its use. So until the next time, I'll bid you peace, and I'll be talking to you again real soon.